Swayam Prabha. Digital India. Educated India.
Welcome back. So, let us continue our discussion on the solid propellant rocket. In the previous class, we have discussed about various terminologies related to solid propellant rocket, starting from the grain and grain configurations, what are the different types of burning profile like progressive, regressive, neutral, how the burning profile can actually depend on the different types of configurations. It can be like cylindrical, it can be square shape, it can have multi hole, it can have wagon wheel structure, it can have star shape geometry, it can have rod and tube. So, depending on the various configuration, the burning profile may change. We also have talked about that the radially outward or radially inward type of burning or longitudinal burning, they are generally termed as the two dimensional grain. Now, the combination of the radial burning and longitudinal burning, sometime they are referred to as the three dimensional grain. If you look at these grain pictures, these are like combination of both radial and longitudinal burning profile. So, it can have like conocyle. So, it is a combination like cone and cylinder. It can have fin and cone, combination of fins, you can see different fins is there. So, it is a combination of cylindrical grain with fin structures in the grain geometry. So, it is termed as the phenocyle. Then it can have like spherical type of grain configuration, which is of course have some slots and cylinders. So, they are we can consider them as the three dimensional grain, because they are a combination of the radial burning and longitudinal burning profile. For other type of like cylindrical grain or the end burning grains, those are although the grain itself are three dimensional in nature, but depending on their radially inward or radially outward or even longitudinal burning profiles, they are actually considered as the two dimensional grain, but where there is a combination of both radial and longitudinal burning profiles, they are termed as the three dimensional grains. Okay. Having said that, now we want to look at further with the very simple burning profiles we have just seen, like for example, like the cylindrical grain. So, if you look at the cylindrical grain, we have seen that the internal perforation is cylindrical. So, if you look at the other view of it, in a simplistic structure we can say this is the grain. So, let us say we draw the rocket also. So, the cylindrical grain is having the nature of radially outward burning. So, it is burning radially outward, and we have already said earlier that since it is radially outward, the burning surface area is increasing over time. So, the pressure and thrust both will increase over time. Now, if you look at carefully what exactly it is happening, that the surface is actually regresses over time. So, at certain time instant, from the initial surface to delta t time instance, it will reach to another surface area. After certain instant of time, it will reach to another, then it will keep on moving until it reaches to the case wall or the inner liner of the casing. In case of burning of rocket propellant grain, the regression rate or the burning rate is termed it is generally measured in terms of length regression over time, like what is the length regresses over certain period of time. So, and it is termed as R, and it is given as the length by time, like how much millimeter or how much centimeter per second it has regressed over time. So, that way it is basically a linear regression rate, you can say that how much millimeter per second has regressed. This is called the regression rate or burning rate of the propellant. Now, from there one can actually understand that if we know the regression rate, since it is a millimeter per second or meter per second, if we know the burning surface area, we can actually get to know the mass flow rate with respect to the burning rate or the regression rate into the burning surface area into the propellant density. So, if the burning surface area remaining constant, we can actually get R into A B into rho A, we can get the mass flow rate. If this is also constant, we can easily get it. For example, like if it is an N burning rocket, we can say the burning area remain constant, like it is burning regressing like this. So, A B is fairly remaining constant. So, we can actually get the mass flow rate also kind of constant, because that is the product of combustion which is going to come here, and that is going to expand in the nozzle. Same thing here, the flame will stay somewhere over here. So, the product of combustion will come here and they will expand, the product gases are going to expand through the nozzle. So, this is the nozzle. So, we can relate the mass flow rate with the burning rate or the regression rate, because since it is a linear one, this will give us the mass flow rate of the or the mass regression rate of the propellant. Okay. Now, this can be related to depending on the type of burning, whether it is going to increase, decrease, that will definitely tell us the value of R. Type of propellant, not all type of propellant will have the same burning rate. There are propellants which can burn faster or which can burn little better compared to the other propellant. So, depending on the ingredients, of course, this burning rate is going to change. Now, coming back to the simple simple grain configurations as we talked about, one is the of course, the cylindrical grain configuration. So, where the internal perforation is a cylinder. So, if you look at this one, it will keep on burning like this. The evolution of burning surfaces will continue like this and it will go on. Okay. So, one can define the initial burning surface area as ABI equal to pi di into L. The final burning surface area can be defined as the pi, the final diameter into L. In between, if wants to know that, one can actually do that in between, let us say intermediate. So, we need to know the intermediate diameter there and that into L, and if there is a delta amount of burning has taken place like the. So, what is the wave thickness here? The wave thickness here is B, as we have already defined in the previous class. So, this is the wave thickness. Okay. So, for a different time instance, if we know the burning rate from the initial to the that time instance, one can actually get the average burning rate. For example, like let us say I want to know that how much time it has taken for delta thickness of the propellant burnt, what is the time duration. So, what you need to know is we need to know the average regression rate for these time instances. So, we first find out the value of Ri, the initial burning rate, and for that matter we need to know we need to know the time period for that. So, we need to find out the what is the burning rate was there for that first one, then the burning rate was for that particular distance r delta, let us say. So, one can find out the average of the burning rate from there by taking this 1 by 2, and from there they can get the time instance for that taken for delta instances, delta thicknesses is like delta by r. One can find out the time duration taken for burning the delta thicknesses, it is like that. Okay. So, definitely one can look at various grain configurations and try to analyze the things by considering the burning rate. So, we will look at the very simple configurations, like one is the circular one, which is the cylindrical grain configurations. So, we can actually get the time duration taken for delta thickness to burn. Similarly, one can actually look at the other configuration. For example, if we have, let us say, square configuration. Once we say the configuration, means we are talking about the internal perforation, the nature of the internal perforation. So, initial cross section is the configuration. So, which is square, let us say the each side is like B. Maybe we can just define in other, we can define this slightly different way, because we have already defined wave thickness as B. So, let us make it as H. Remember, the length of the grains, which is the other side of the board. So, here the length is like, as you said, L. That is why we got the initial burning surface area as pi di into L. Here the final burning surface area was pi df into L. Now, what about the case for the square configuration? If we are asked to find out the initial burning surface area, what can we write? We can write the, you see, it is extended over the length L. If the grain has the length of L, each of this H into L, that is the H times L each side of it. So, there are 4 of it. So, we can simply write 4 H L, that is our initial burning surface of the grain. Now, we can consider at a different time instance, for example, like since the initial time, sorry, at the first instant the initial burning surface area, we are getting like 4 H into L. So, this is like initial burning surface area. Now, if you look at, let us say there is a delta is the wave thickness. So, if we keep on moving with this grain, it will reach to maximum to the liner or the casing, inner casing of the motor. So, it can reach up to here. So, if this is the thickness, let us say is delta, we can get the final burning surface. You see, if we draw it properly, initial burning surface was like this. So, the square will remain square till the end, but as you said the corner will become rounded. So, it will be like this. Something like this. So, this B will become still will have H will have H here. So, this is H, this is H, this is H. So, the initial, as we had 4 H into L, that will be there 4 H L, plus we have to consider this part, which was which we can get like, this is like delta f we had sorry delta we have defined there. So, this is the radius. So, we can get like 2 pi r by 4, that will give us the perimeter of the circle, because this is like a arc. So, we need to know the length of that. If we consider the length of that, we have 4 of them 1, 2, 3 and this 4. So, if we do that, we have like 2 pi into delta L. So, that will give us the final burning surface area. This was the initial, this is the final burning surface area. Okay. So, one can easily find out the what is the burning surface area if we know the value of H and value of L. So, some numerical problem one can try that, let us say after a certain time instant it has reached to the value delta or the wave thickness is delta, what will be the final burning surface area, we can easily find out from there. Now, there are some grain configuration which is a combination of this square shape and the cylindrical shape. So, we have to use the combined form of this based on the geometry, and we can use this evaluation of burning surfaces and we can actually get the final burning surface area. Now, if you look at this burning processes, as we said earlier that there will be some amount of propellant which will be left out even after the final burning. So, this is like left out propellant. So, it will burn till the wave burning is which is the delta. In case of this one, this was the wave burning B. We could have defined this as B also, because as per our definition wave thickness was B. So, we can write this as B also, since we have already defined this as H. So, it can be B. So, 4 H L into 2 pi B L, that is the final burning surface area. Now, as I said, the burning will continue till it reaches to the inner wall of the casing, but if the pressure and temperature is high enough, this remaining propellant which was actually the sliver may also burn. So, if you look at the typical pressure time profile, or the even if you just simply plot the burning surface versus time, what we can get initially the burning surface. So, it is starting from the initial surface area, it is still keep on continuing till it reaches to the final burning surface, and then if the pressure and temperatures are high enough, the sliver may continue to burn. But if you look at the sliver will not having the progressive nature, means the surface area is not going to increase further, because we are looking at the sliver which is something like this. So, as the burning continues, the surface area will keep on decreasing. So, this is the sliver is going to burn, but it will reduce the surface area. So, the surface area is going to the surface area is going to reduce. So, this part of burning which was basically burning the wave. So, this is called the wave burning, and this part is called the sliver burning. Okay. Of course, sliver is not the intended for the solid propellant, because this is the remaining unburned propellant. It is actually changing the intended burning profile if the sliver is remaining. Okay. This is a simple configuration, that is why we are able to tell you that this is happening like this, but there are some complex geometries where in different corners there will be some remaining sliver. So, which will gives the different burning profile, and that will actually influence the pressure time or thrust time curve. So, in general in design practice is like we do not want any sliver to be present after the full burning duration. So, sliver is not intended, it is like the unburned propellant. Okay. One can actually do some some calculations with this and try to find out that how much sliver is remaining after the wave burnout. like after wave burning, if we know some of these parameters like value of H, value of L, and then we can know the burning time. After that, we can calculate that how much amount of sliver is remaining after the wave burnout. Okay. Now, the another configurations, as we said, was the star shape configuration. So, okay. So, depending on the number of vertices, we can have like if n number of vertices, n vertices. So, it will have 2n flat surfaces. Okay. Like 1, 2, 3, 4, 5, 6. So, it is like 6 pointed star. So, we have 12 flat surface. Flat surface means we are talking about these are the surfaces. For each vertices there are 2 flat surfaces. So, if you look at, they will keep on burning like this, like this. So, one can actually try to see that how the burning profile will depend on the number of vertices and number of flat surfaces, the angle between them, how they are actually going to influence the burning profile of the star shape. So, this is like star configuration, star grain configuration. Since the as I am repeating many times now, that since the focus of the course is on the combustion of solid propellant and fuel, we are not going into the details of the rocket propulsion side, like the internal ballistic of the rocket. So, I would rather request all the participants to refer some of the materials available in the basic rocket propulsion book or even the NPTEL lecture materials, where these different configurations are discussed and how the evolution of burning surface take place. Those are pretty much discussed in those courses or even in the lecture materials. So, please refer to those, that depending on the number of vertices, the angle subtended by them, like what is the angle, let us say it is angle theta, number of vertices is n, how they influence the burning profile, either progressive, regressive or even neutral. So, the star shape configuration can have all three profiles, either progressive or regressive or even neutral, depending on the number of vertices and the angles subtended by their flat surfaces. Okay. So, please look at some of the previous study materials, where you can understand that how they are influencing the burning profiles. So, I think we will not go further on the grain configurations. I am just leaving it to the participants to revise some of the materials, so that we can come back to the main track of the course, and we will focus more on the fuels and propellants used for solid rocket. All right. So, let us try to look at the various propellants used for solid rocket. But before moving into that, we have talked about one thing which is called the regression rate in the previous lecture, rate R. So, I may forget later on, I should at least mention here is that the regression rate is the length regression over time. So, it is like millimeter per second or meter per second, but it is defined as the length regression, like if it is a radially outward burning. So, it will like how much radius has regresses over time. Okay. So, now the question is how it is defined, how it is determined that how much millimeter per second has regressed. for a particular propellant. So, there are different testing methods. Choosing a certain propellant, of course, it will very much tricky. In order to choose certain propellant, we need to understand the burning rate, like how the propellant is burning. So, there are different methods used step by step, like very initial method is the stand burning experiment or stand burner. Using stand burner, it is sometimes known as the Crawford stand burner or Crawford bomb, where the strand is actually allowed to burn inside a pressurized chamber. So, a small propellant strand it may be ignited by the ignition coil. There may be optical section to view it, various modified configuration of this setup is available. Of course, it is pressurized with nitrogen. So, at a different pressure it allow the propellant strand to burn. So, this is propellant strand. There may be some fuse where located at a specified length L. So, as the burning surface regresses over time, so the outer surface of the propellant is inhibited, means it will only allow to burn from this surface only. So, the burning will proceed like this. So, once it reaches to the first fuse where it will got cut, it will be start the timer unit. So, maybe this is connected with a timer unit which will note the time until it reaches to the second where it will give the time delta t. From there, since the fused wires were located at a specified length, one can find out the value of burning rate by dividing the length over time by time. So, that way one can understand the regression rate for that particular pressure. Now, one can actually do it for various R1, R2, R3 and so on at different pressure, and it can be found out at various pressure how the burning rate is varying. Now, why I am telling this thing, because we have brought about this important parameter R, we can later on see that how this burning rate is very much dependent on the pressure once we talk about the mechanisms of the burning mechanism of various propellants. Now, this is one method. The other method is like small ballistic motor, where we can actually use a static rocket. Static rocket means we do not allow it to go away, it is like hold, and we allow it to burn. So, it will regress, and from there actually we can calculate the regression rate. So, the first stage of the testing is the strand burning. So, this requires small amount of materials, it does not need to be of very high cost. So, this is the first step for the propellant development. So, if we choose the different ingredients, immediately after that we will just do the burning rate evaluation by using this Crawford burner or stand burning test. Then once we have enough confidence, we at least get the burning rate versus pressure profile, and we know that how the burning rate is changing over different pressure values. We can go to the small ballistic motor test, and there we can look at the thrust time profile, pressure time profile there. Then finally, if they are satisfied, this will go for further testing, like the with flight testing with instrument. It may be like semi instrumented, but the flight testings with that type of propellant is carried out for that particular rocket with instrumentations. Okay. So, these are the various testing methods since we talked about this one. So, that is why it is very much relevant. So, we first begin with this Crawford-Warner test to know how the different ingredients are playing an important role there. So, now we are in a state that we can at least understand that the burning of the propellant, how it is important, because it is influencing the eventually the performance of the rocket. And the burning of the propellant means we are talking about the burning of the propellant grain. Now, we are going to discuss that what are the different ingredients which are going to be essential, or there are certain ingredients which are going to influence the burning rate of the propellant. So, our next topic of discussion will be the solid propellants. Okay. So, this is going to be we will begin this next module like solid propellants in the next lectures, but we should remember that as you said the propellants, it must have like the fuel and oxidizer, because since rocket is not taking any oxidizer from the atmosphere, it must carry its own fuel and oxidizer there, and since it is a solid propellant, the fuel and oxidizer are mixed together. If you recall our introductory class where we have talked about the different type of rockets, solid rocket, liquid rocket and hybrid rocket, we have seen that for liquid rocket the fuel and oxidizers are stored in a separate tanks and they are supplied through some turbo pumps, whereas in case of solid propellant the fuel and oxidizer are mixed intermittently and they are made to have a shaped mass, which we now know it is called grain. So, basically the solid propellants are must have the combination of fuels and oxidizer plus other ingredients. So, in the next class we will start looking at what are the different characteristics of the propellant which are kind of need to fulfill. So, the choice of what are the requirements to be fulfilled by the propellant in order to have them in the propellant grain. So, the criteria for selection of the propellants that we will discuss in the next class. Okay. Thank you.